Chapter 7, Rocks and Minerals. Today, I'm going to discuss earth scientists, who are nature detectives, elements and atoms, the basic building blocks, minerals, igneous rocks, sedimentary rocks, metamorphic rocks, and the rock cycle and mineral resources. Earth scientists are nature detectives. Example: are the rocks on Mars the same as the rocks on Earth? And why would a scientist want to know the answer to that question? Understanding rocks enables scientists to locate mineral resources, for example, copper and gypsum, to find fossil fuels like natural gas, coal, or oil, to assess the risk from natural hazards such as volcanic eruptions and tsunamis, to learn about Earth's processes such as plate tectonics, and to discover the history and origins of other planets. Scientists didn't always think that there was a rock cycle. There were other ideas about how rocks formed. Neptunism, where scientists thought that rocks formed in a global ocean when the material sank to the ocean floor or was precipitated from chemical reactions. Or Plutonism, where they thought that heat from the Earth's interior melted the rocks or caused them to fuse together. Ideas change, evidence changes. When new evidence is presented, it changes the ideas. Bricks are manufactured materials with some of the same characteristics of rocks, and that can provide clues to the rock formation processes. Bricks are made from raw materials such as shale or fire clay found at the Earth's surface. Variations in the composition of raw materials produces different brick colors. Red bricks contain more iron. Where do bricks come from? Well, raw materials are smashed into smaller pieces in a crusher. The crushed material are ground even smaller by a grinding wheel. The resulting particles are passed through a series of screens to sort the material by size. Sugar and flour-sized particles are mixed with water and other ingredients. Then, small particles are mixed with water and other ingredients. The wet mixture is forced through a brick-shaped form. The wet bar is cut into smaller brick-sized pieces. Excess water is removed by passing wet bricks slowly through long dryers. And the temperature is about 200 degrees Celsius. The final stage is the firing of the bricks in a kiln at high temperatures at about 1100 degrees Celsius. Fist-sized rocks are shown here. The fine particles on a conveyor belt after they've been ground. Here's the long chocolate bar of the wet clay mixture before they cut them into brick-sized pieces. And here are the finished bricks coming out of the kiln. Brick making, like rock formation, involves the physical disintegration of raw materials, chemical changes, and thermal effects. And brick making is influenced by the composition of the raw materials, just like the formation of rocks. Rocks are made of minerals. There are about 20 common minerals. For example, the rock granite, shown in the next photo, is composed of 4 key minerals: feldspar, quartz, mica, and amphibole, and minor amounts of others. It's a photograph of granite. Minerals are made of elements. 8 common elements compose 98% of continental crust rocks. Some minerals, for example quartz, are composed of just 2 elements. Others are made up of several elements. Some elements occur more frequently than others. The most common minerals in granite are quartz, feldspar, mica, and amphibole. This table shows common elements in the continental crust: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, and others. It also shows the percentage of each element that are found and how we use some of these elements. The atom is the smallest particle that retains the characteristic of an element. They're made of electrons, protons, and neutrons. Atoms are made of protons, neutrons, and electrons, and the protons and neutrons are found in the nucleus. The electrons orbit the nucleus in sort of a cloud. The atom is the smallest particle that will retain the characteristic of an element. For instance, here's helium, and it has 2 protons. This is neon. Neon has 10 protons. This represents, the black lines actually represent the path that an electron might follow. They don't necessarily go along the same path. They might go like this. They might turn like that. They go the same direction all the time, but not necessarily in the same path. The atomic number is the number of protons in the nucleus. Each element has a different number of protons in the atomic nucleus. For example, neon has 10 protons and helium has 2. Atoms may have a negative or positive charge if they gain or lose electrons. Ions are atoms with different numbers of protons and electrons. Oxygen can gain 2 electrons to fill vacant places in their little orbit. 8 protons, 10 electrons yields -2, a negative charge. Silicon can lose 4 electrons to yield a positive charge of +4. These orbits, or shells they're called, have a certain number of spaces available. Oxygen has 2 vacancies. Silicon has another shell, so there's 1, 2, 3 shells right here. 2 electrons are on the inside shell, 7 on this shell. And then there are 4 vacant sites that need to be filled on the outside shell. The elements bond together to form minerals. An ionic bond is a balance of negative and positive charges of different ions. And that depends on whether it's got vacant spots on the outside shell or not. Covalent bonds are when electrons are shared between elements to achieve a stable atomic structure. Covalent bonds, the sharing of electrons between elements. This achieves a stable atomic structure. Let's say that one atom has the correct number of electrons in its outer shell, and there's another atom right next to it that does not. It has a vacant spot on its outer shell. They will share one of the electrons. Therefore, they're bonded together. They stick together because they're sharing one electron. Ionic bonds is a balance of negative and positive charges. Sodium atom loses an extra electron to yield a positive charge. A chlorine ion gains an electron to produce a negative charge. Sodium and chlorine will bond together to form rock salt. An ionic bond is a balance of positive sodium ions with negative chlorine ions. This shows two shells. This is sodium. The nucleus has 11 protons. The inner energy level, or shell, has 2 electrons. The outer has 8. This is chlorine. It has 2 on the inner shell. The inner energy level filled with 8 electrons. The outer energy level contains 7 electrons. It has captured an electron that's needed to fill the outer energy. And where did it get it from? It got it from the sodium. And this is salt. Covalent bonds, the sharing of electrons between elements. Oxygen is 2 electrons short of having 8 to fill its outer energy level, or shell. The hydrogen and oxygen atoms share electrons to give oxygen an outer energy level of 8. And the hydrogen have 2. What is 2 hydrogens and 1 oxygen? H2O. Hydrogen and oxygen bond together to form water, H2O. They have covalent bonds. They share electrons between atoms, ions. The arrangement of atoms in silica tetrahedron. Multiple bonds can be made. Silicon and oxygen joined together by a combination of ionic and covalent bonding. 4 oxygen and 1 silicon atom combine by covalent bonds to form a silica tetrahedron. Tetrahedron has a negative charge, and it forms ionic bonds with atoms of other elements. Silicate minerals contain both silicon and oxygen. Silicon and oxygen are most common elements in the crust. Silicates are the most common mineral group too. Examples are quartz, feldspar, mica, and amphibole. Different types of bonds result in minerals of different strength. Ionic bonds, think of a Velcro. They can be broken pretty easily. Covalent bonds are stronger. It's very difficult to break oxygen away from hydrogen in water. Minerals formed with covalent bonds are stronger and more resistant to the destructive forces at Earth's surface. Silicates form more resistant rocks than most other mineral groups. Elements and atoms. An isolated silicate. Here's the structure and the mineral example. It's alone. A single chain. A double chain. A sheet silicate. A framework of silicate, like quartz and feldspar. Silica tetrahedron combined together in different patterns in different silicate minerals. Minerals with low silica content have very simple structures, like olivine or amphibole. Minerals with high silica content have more complex structures, like quartz and feldspar. Minerals are naturally occurring inorganic solids of one or more elements that have a definite chemical composition with an orderly internal arrangement of atoms. Diversity of minerals: quartz, muscovite mica, orthoclase feldspar, galena, pyrite, halite, galena, pyrite, and halite all exhibit a cubic crystal form. Galena and pyrite have a metallic luster. This is quartz, mica, and feldspar. Galena and pyrite. This is halite. A crystal form means the arrangement of the faces of a crystal to form a particular shape. And the shapes are as follows: prisms, pyramids, needles, cubes, and sheets. And here are some examples. Hardness. Minerals ranked by their relative hardness using the Mohs hardness scale. The harder minerals can scratch softer minerals. Softer minerals are more likely to break down at Earth's surface. More resistant minerals are more likely to be preserved, like quartz sand on beaches, which would mean gypsum can scratch talc. Fluorite can scratch gypsum. Feldspar can scratch any of these. Topaz can scratch anything above it. Diamonds can scratch just about anything. Minerals have characteristic colors. There are dark minerals: black, brown, dark green, olivine, amphibole, pyroxene, biotite, mica. There are light-colored minerals: white, gray, pink. Quartz, feldspar, muscovite, mica, calcite. But be careful in trying to identify a mineral by its color, because they can have many different colors. Quartz is not just white or pink. Luster, streak, and reaction to acid. A streak, a color mark on unglazed porcelain. For example, hematite will leave a brown streak. Here's hematite scratching porcelain, leaves a brown streak. Luster, how light reflects on the mineral. For example, the metallic luster of iron pyrite. When weak hydrochloric acid is added to the mineral calcite, a characteristic reaction becomes visible. Cleavage. The minerals break along planes of weakness defined by atomic structure. It's in one direction, two directions that intersect at 90 degrees angles, two directions that do not intersect at 90-degree angles, three directions intersecting at 90-degree angles, three directions not intersecting. There are A would be in one direction. This one is two directions that intersect at 90-degree angles. This one. Two directions that do not intersect at 90-degree angles right here. You can tell this is not 90-degree angles. This one is, but that one's not. You can see how it would make the shape look a little different. This would be two directions that do not intersect at 90-degree angles. This one intersects at three places at 90-degree angles. This one intersects at three places, not at 90-degree angles. This is an example of a diamond intersecting at four places at 90-degree angles. This one has 6 places where they intersect. Atoms to rocks, how they fit together. A rock is an aggregate of minerals. The structure, texture, and type of minerals depend upon the conditions of the formation of the rock. Quartz, for example, is a mineral, is a physically and chemically distinct part of a rock. It has properties you can see with the unaided eye, such as color and cleavage. Each type of mineral also has its own orderly internal crystalline structure at the atomic level. This explains the physical properties seen at a larger scale. In this example, showing quartz, the large oxygen atoms enclose smaller silicon atoms. We construct models of some crystal structures linking the centers of oxygen atoms together to form silica tetrahedra. This helps us envision the geometric beauty of a mineral's atomic arrangement. An atom consists of a cloud of electrons at different energy levels, or shells, enclosing a tiny nucleus. An atom's nucleus is a swarm of protons and neutrons at the core of an atom. The origin of rocks. Examine these objects. On the basis of observation only, how would you classify these objects into different groups? Color, shape, size. Two types of igneous rocks are classified based on texture and composition. The same magma can form both rock types. Volcanic rocks form when magma rises to Earth's surface. This produces volcanoes, lava flows, tephra. Molten rock cools very rapidly, so that's where igneous rocks come from. Examples: batholith, stock, sill, dike, laccolith. Plutonic rocks, the second type of igneous rocks, form when magma solidifies below Earth's surface. It produces plutons that remain hidden until exposed by erosion. Molten rock cools very slowly. The texture, the size of crystals of minerals in igneous rocks depends on the rate of cooling of magma. Rapid cooling produces microscopic crystals. Slow cooling produces large, visible crystals. Crystal size interpreted to learn where rocks are formed. Graphic showing rapid cooling and slow cooling. Examples of igneous rocks: granite, up here, basalt, andesite, rhyolite, less viscous, low silica magma likely to reach the surface to form volcanic igneous rocks, for example, basalt. More viscous, high silica magma likely to cool below the surface to form plutonic igneous rocks, for example, granite. Granite batholiths in the Sierra Nevada mountains in California. The crystallization of silicate minerals from magma is what's shown on this graphic. This is rock. This is the type of rock that's produced, and the crystallizing minerals and their silicate structures. Sedimentary rocks form as horizontal layers or beds. They're identified based on composition, thickness, the oldest bed at the bottom, the youngest at the top. There are 3 types of sedimentary rocks: clastic, chemical, and biochemical. These are identified by the materials that make up the rock and or the process by which they formed. Clastic sedimentary rocks. The generation of them, the physical and chemical breaking down of any rock at Earth's surface, or the weathering to form the sediment. The transportation. Erosion can move it. Erosion yields sediment moved from place of origin by streams, wind, and glaciers. The sediment generated by the weathering of Himalayas and transported in the rivers. Sediment or dust transported by the prevailing winds from Africa toward the Atlantic Ocean. Clastic sedimentary rocks, lithification. Sediment deposited when velocity of transport medium decreases. The larger grain sizes are deposited first. The finest grains remain in suspension and are deposited last. Over time, the sediment is slowly compacted and the grains are cemented together to form a new rock, lithification. This is the deposited sediment of contrasting grain sizes. Clastic sediment and clastic sedimentary rocks. Rock names reflect the grain size. Mudstone, shale are made of clay, which have silt-sized grains. Sandstone have sand-sized particles. A conglomerate is made of gravel and larger fragments. The rock names reflect the grain size. The transportation process sorts grains so deposits may have characteristic grain size. For example, sand on the beach. This graphic shows the grain size and what types of rocks. Clay has a grain size of less than 0.0039 millimeters. And the type of rocks would be shale and mudstone. Silt. Notice that they're not very creative with the names here. Silt and siltstone. Sand and sandstone. Gravel, a conglomerate, a mixture of things. ranges from rice grains to orange size. It's a conglomerate. It's a conglomeration. Clastic sediment and clastic sedimentary rocks. Transportation process sorts grains so deposits may have characteristic grain size. For example, sand on a beach. Sedimentary rocks hold clues to the environment where they're formed. For example, river channels, a high velocity flow in floods, gravels, a conglomerate. A moderate speed would be sand and sandstone. The slow flow river channels would have a lot of mud and shale. Chemical sedimentary rocks form when minerals precipitate or crystallize from a solution as a result of changing physical conditions. Solutions equals fresh water in lakes, groundwater, or seawater. Changing conditions commonly equals increased temperatures or evaporation. Salt deposited on the floor of an ancient Lake Bonneville in Utah. Sedimentary rocks. These can be readily dissolved in water and transported to oceans. Rocks are typically indicative of shallow coastal marine conditions in the geologic past, termed evaporites, as most form by precipitation due to evaporation. Biochemical sedimentary rocks link the biosphere and the geosphere. They form due to actions of living organisms that cause minerals to be extracted, or they form due to actions of living organisms that cause minerals to be extracted from solution or from the remains of dead organisms. A coral reef is actually alive and has skeletal structures. There are corals, which are little polyps, and underneath the polyps would be the skeletons. Biochemical sedimentary rocks may form from the remains of dead organisms, such as corals. Coquina yields limestone formed from broken shell fragments. Coal yields carbon-rich rock formed from compacted plant remains. Examples of sedimentary rocks. There's a conglomerate. They may form from the remains of dead organisms. Chalk formed from billions of coccoliths, round plates of calcite from microscopic coccolithore organisms. Chalk is an example of limestone, places where the coccolithore bloom. The world is heavily dependent on oil and natural gas. The form from buried organic rich sediments. Chemical reactions convert organics with increased pressure and temperatures of between 50 to 100 degrees Celsius. Over time, and we're talking millions of years, oil and gas can form. Oil and gas may be trapped to form hydrocarbon reservoirs. Sedimentary rock and fossil fuels. The U.S. has some of the largest coal reserves in the world. Coal was formed from buried plants, and over time, millions of years, coal can form. The coal type depends on the organic content of the parent material, the burial depth and the heat. Lignite, the low grade, bituminous, the medium, and the anthracite, high grade. Metamorphism. Changes in mineral composition and texture that can occur in any solid rock. Changes due to increasing temperature and/or pressure and/or the presence of fluids. Temperatures high enough to promote chemical reactions but not high enough to cause melting. And that would be approximately 200 degrees Celsius to 1100 degrees Celsius, depending on the rock type and the conditions. And similar temperatures found deep in the crust or near magma chambers. There are two types of metamorphism. Contact metamorphism, changes due to increases in temperature where rocks come into contact with a heat source, for example, the magma chamber. An example would be limestone around a magma chamber is baked by heat to form marble. There's an example of marble and limestone, and they have similar composition, but marble typically has a larger grain size. Regional metamorphism. Increased heat and pressure associated with plate tectonic processes that form mountains. Increased pressures and temperature cause the tabular minerals to take on a preferred orientation known as foliation, perpendicular to the direction of the pressure. Foliation is produced when tabular minerals grow perpendicular to the direction of pressure. Unmetamorphed, non-foliated original rock, granite, with random distribution of minerals. Metamorphic rock, like gneiss, with foliation illustrates parallel alignment of minerals. Rock cycle links igneous, sedimentary, and metamorphic rocks together. Any rock can become any other type of rock under the appropriate conditions. Mineral resources result from specific geologic processes associated with formation of rocks. It can result from chemical reactions driven by changing temperatures and the movement of fluids through the rocks. Mineral resources result from specific geologic processes associated with formation of rocks. It can result when the minerals crystallize at different temperatures. It can also result from concentration of various types of rocks and minerals during erosion, transportation, and deposition. And this concludes Chapter 7.